Hello everyone, I hope you are all doing well. I am Tamer Hassan Fahim, Assistant Professor at Engineering Mathematics and Physics Department, Faculty of Engineering, Alexandria University. I am going now to present my research paper entitled Optimizing Age of Information for Energy Harvesting Systems using an Energy-Aware Hybrid Preemptive Non-Preemptive Disciplines, co-authored with Professor Ahmed Abdel Malik, Professor Wahid Zahra, and Professor Sharif Rabia. The outline of our presentation is divided as follows. A brief introduction to real-time status update systems, the motivation and the corresponding objectives, the proposed system description, the performance analysis of our work, the numerical results, and finally, conclusion and our future work. So let's give a brief introduction to real-time status update systems. Recently, smart IoT systems have been widely deployed in real-life applications. All these applications have a common communication paradigm, that is, real-time status update systems. In such systems, transmitter sends status update packets about the physical process of interest through the network to the interested recipient. The received packets are processed for monitoring and control purposes. Accordingly, in such systems, receiving outdated packets leads to inaccurate monitoring and control decisions, which degrade the system reliability. Accordingly, information freshness is a critical quality of service requirement for such systems. It is well established that maximizing information throughput or minimizing information delay don't imply enhancing information freshness. Accordingly, a new metric called the age of information has been coined to quantify information freshness. Age of information is a monitor-related measure which reflects to what extent the information at the monitor is outdated with respect to the information at the transmitter. And it can be mathematically formulated as T minus G of T, where G of T is the generation time of the latest packet received at the monitor. However, in more practical situations, real-time status update systems may have energy constraints for status update packet transmissions. Consuming the total energy power leads to interrupting the transmission and thereby degrading information freshness. Accordingly, to ensure system reliability, energy harvesting modules may be used in the transmitter end to collect energy from the ambient resources. For the motivation and the corresponding objectives, first, we found that the classical service disciplines, preemptive and non-preemptive disciplines, are mainly deployed in the age of information literature of energy harvesting enabled systems. In such disciplines, the fresh arrival request to replace the outdated packets in the server can be admitted or declined. Moreover, one energy packet is consumed upon each service preemption. Accordingly, the preemptive discipline may enhance information freshness at the cost of increasing energy depletion. On the other hand, the non-preemption discipline may degrade information freshness to save energy resources. So there are two main drawbacks for such disciplines: the trade-off between information freshness and energy utilization, and the inadaptability to variation of energy data profiles. Accordingly, we aim to redeploy discretionary preemptive disciplines, or so-called hyper-preemptive non-preemptive disciplines, where the preemption can be admitted or declined based on specific discretionary rule at the server. For the second motivation point, we found that the age of information study of the hyper-preemptive non-preemptive discipline has been addressed for energy unconstrained systems. Accordingly, we aim to propose a new hyper-preemptive non-preemptive discipline dedicated for energy harvesting enabled systems. Accordingly, our main contribution is that we propose an energy-aware hyper-preemptive non-preemptive discipline for a single source systems, and to the best of our knowledge, it is the first time to consider such a hyper-discipline as a packet management scheme for energy harvesting enabled systems. For the proposed system description, we consider an energy harvesting enabled single source, single server system. We assume Poisson arrival process for status update packets and Poisson arrival process for energy packets and exponential service time distributions and a finite battery with capacity P. To demonstrate the proposed system dynamics upon any fresh arrival of status update packets, let's consider the following flowchart. If the server is empty, the admission is accepted if at least one energy packet exists on the battery. If the server is busy, the proposed energy-aware hybrid discipline is deployed to control service preemption. In such a case, the preemption is only admitted if the energy of battery exceeds a predetermined threshold. This threshold acts as a controlling parameter for our discipline, and the extreme cases of this threshold represent the full preemption and the non-preemption disciplines. For the energy replenishment process, we consider two harvesting modes: energy harvesting when idle and the energy harvesting anytime. It depends on the possibility to harvest energy and serve a packet at the same time or not. For the energy depletion process, one energy packet is consumed upon each service completion and each service preemption. For our performance analysis, we analyze the average age of information and the average energy packet loss rate under general setting of our system parameters. We deploy the stochastic hypersystem approach. In such an approach, the system descriptor is a hybrid of discrete state representing system occupancy and the continuous state representing age of information tracking process. In our case, we have a two-dimensional discrete state space to track the server availability and the battery energy level, and two-dimensional age information tracking process to track the age information signal at the server and the monitor. For the discrete state dynamics can be modeled as two-dimensional continuous time Markov chain, whereas the age of information signals typically increase linear with time, and then upon the occurrence of certain stochastic events, they may reset to some lower value before increasing one more time. This resetting is linear and can be mathematically formulated as matrix transformation equation. We construct a stochastic hypersystem transition table which contain all discrete state transitions and the corresponding age of information resetting. For the discrete state transitions, we have the following stochastic events: energy replenishment when the server is idle, energy replenishment when the server is busy, successive service completion to the monitor, update packet arrival at empty server, update packet arrival at busy server. For the age of information resetting, we have the following stochastic events: fresh arrival entry to the server and departure to the monitor event. Otherwise, there is no change in the age of information process. We evaluate station state probabilities using global balancing equation and the normalization equation, and then evaluate correlation vector VQ, which contain the average age of information signals at the server and the monitor. And finally, we can evaluate the average age of information at the monitor using this formulation. In the second analytical study, we evaluate the average energy loss rate due to service preemption, where upon each service preemption, we have a one energy packet lost. Accordingly, we can evaluate the average energy loss rate using this formulation. For our numerical results, we conduct an age of information optimization problem to minimize the average age of information using exhaustive search methods to find the optimal threshold parameter and the corresponding average age of information and the energy packet loss rate. Under a specific numerical setting, we analyze the findings of this optimization problem through three different studies. In the first study, we analyze the behavior of the optimal threshold parameter across energy data profile for the two harvesting modes under study. As shown in these results, we have the following observations. First, the full preemption discipline is not always optimal for energy harvesting enabled systems. In contrast with systems with no energy constraints, where the preemption discipline is always the optimal scheme. Second, when the data rate is significantly greater than the energy rate, which reflects the energy pool regime, the optimal threshold parameter approaches the full non-preemption discipline, and thereby enhancing the energy utilization of this mode. On the other hand, when the data rate is significantly less than the energy rate, which reflects the energy reach regime, the optimal installation parameter approaches the full preemption discipline and is thereby enhancing age of information without risking energy depletion. Moreover, there is an intermediate region across the energy data profile where the hyper-preemptive non-preemptive discipline is the optimal, particularly in the energy harvesting anytime mode. Accordingly, we can conclude that the optimal energy-aware hyper-discipline is efficiently adaptable to the variations of data and the energy profiles. In the second study, we analyzed the age of information gain achieved by the proposed model relative to the preemption and the non-preemption disciplines. In this table, we summarize the age of information gain for the two harvesting modes and under specific settings of the energy data profile. For the first observation, we found that the proposed model achieves up to 30% age of information gain relative to the non-preemption discipline. And this gain increases near the energy reach regime. Second, the proposed model achieves up to 8% age of information gain relative to the full preemption discipline. And this gain increases near the energy poor regime. Third, the age of information gain in the energy harvesting when idle mode is lower. This is due to the limited energy resources of the energy harvesting when idle mode, which restricts the age of information enhancements. In the third study, we analyze the energy loss reduction achieved by the proposed model relative to the preemption discipline, which represents the worst case scenario for energy loss. As shown in this figure, we have the following observations. First, the proposed model achieved a considerable energy loss reduction, particularly near the energy poor regime. Second, in the energy harvesting when idle mode, the proposed model provides a broader range of energy loss reduction across the energy data profile, and thereby enhancing the energy utilization of this mode. For our conclusion, an energy harvesting enabled single source system is addressed considering a limited battery capacity and a limited capacity battery and two harvesting modes. We propose an energy-aware hyper-preemption and preemption discipline with the energy threshold being the controlling parameter. The average age of information and the energy packet loss rate are analyzed using stochastic hypersystem approach. The numerical studies demonstrate the advantages of the proposed model in balancing age of information minimization and the energy utilization and in enhancing the adaptability of the system model. The proposed model particularly enhance the energy utilization in the cases of limited energy resources, that is, energy harvesting when idle mode and energy poor regimes. For our future work, we expect extensions in the following directions: extending the analysis to a more general service time distribution beyond the explanation, extending the energy replenishment to a more general renewal process beyond the Poisson process to capture a more practical situations. Extending the numerical study by addressing the impact of some system parameters such as battery size and by comparing the proposed hybrid discipline with the existing hybrid ones. Extending to the case of multiple sources with priority to capture the heterogeneity in quality of service requirements. This paper is based upon work supported by Science Technology Innovation Funding Authority STDF of Egypt under grant number 48186. Professor Shir Fabia is a project PI. Thank you.